Scientists may have just built a periodic table for artificial intelligence. Artificial intelligence has advanced at an astonishing pace over the past decade. Systems can now analyze images, understand language, generate videos, and combine multiple streams of information simultaneously. But behind the impressive results lies a messy reality. Researchers often rely on trial and error when choosing the algorithms that power these systems. With hundreds of machine learning techniques available, each designed slightly differently, it can be surprisingly difficult to determine which one will work best for a specific task. Now, physicists believe they may have found a way to organize this chaos using a unifying principle that could function as a kind of periodic table for AI methods. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all of the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. The idea comes from researchers who approached artificial intelligence with a physicist's mindset rather than a traditional machine learning perspective. In physics, progress often comes from identifying simple rules that explain many different phenomena at once. Electricity, magnetism, and light were once treated as separate mysteries until scientists realized they were connected through a deeper framework of electromagnetic. The researchers suspected that modern AI techniques might also share a hidden underlying structure. Instead of viewing each algorithm as a separate invention, they asked whether a single principle might explain why so many successful methods work. Their analysis revealed something surprisingly elegant. Many AI systems appear to operate on a basic trade-off. They compress information while preserving the parts that are most useful for prediction. In other words, when an AI system learns from data, whether that data includes text, images, or audio, it doesn't need to retain every detail. What really matters is identifying which pieces of information help predict the correct outcome. Everything else can be discarded. This idea might sound simple, but it turns out to connect a wide range of machine learning techniques that were previously treated as unrelated. To formalize this insight, the team developed a mathematical framework known as the Variational Multivariate Information Bottleneck Framework. The name sounds complex, but the concept is easier to visualize if you imagine a control dial. By adjusting this dial, researchers can decide how much information an AI model should keep and how much it should compress. Different positions on this dial correspond to different algorithmic strategies. Some models preserve more raw data for detailed analysis, while others aggressively compress the data to isolate only the most predictive signals. The framework effectively places these strategies into a structured map, similar to how the periodic table organizes chemical elements. This new structure has several practical advantages. First, it allows researchers to design algorithms more systematically rather than starting from scratch each time they face a new problem. Instead of randomly experimenting with different techniques, they can use the framework to predict which approach is most likely to succeed. Second, the model can estimate how much training data a system will require before it is built. That capability could save enormous time and resources in AI development, where training large models can cost millions of dollars and require vast computing infrastructure. Efficiency is another major benefit. Modern AI systems often rely on huge datasets and powerful data centers that consume enormous amounts of electricity. By focusing only on the most important information, future models could operate with far less data and computing power. That would not only make AI development cheaper, but also reduce the environmental impact of training large models. As artificial intelligence becomes more integrated into everyday technology, from smartphones to industrial systems, energy efficiency is likely to become a critical concern. Beyond efficiency, the framework also addresses a deeper issue in artificial intelligence: understanding why models behave the way they do. Many machine learning systems today function like black boxes. They can make accurate predictions, but the reasoning behind those predictions is often difficult to interpret. By grounding AI methods in a clear mathematical principle, researchers may gain better insight into how information flows through a model and why certain patterns are recognized as important. That understanding could help make AI systems more reliable, transparent, and trustworthy, especially in sensitive areas such as healthcare, finance, and autonomous transportation. Interestingly, the principle behind this framework also resembles how the human brain processes information. Our brains constantly receive enormous amounts of sensory input, from sights and sounds to smells and touch, but they cannot process every detail equally. Instead, the brain compresses incoming information, filtering out irrelevant signals while preserving the patterns most relevant for decision making. If artificial intelligence is beginning to follow a similar strategy, it could suggest that both biological and machine intelligence rely on comparable information processing principles. Looking forward, this framework could influence the next generation of AI research. Instead of building ever larger models with brute computational force, scientists may focus on designing smarter algorithms that learn more efficiently. Such approaches could enable breakthroughs in areas where data is scarce, including scientific research, medical diagnostics, and environmental monitoring. It might also make advanced AI tools accessible to smaller organizations that lack the resources to train massive models. Ultimately, the idea of a periodic table for AI is more than a clever metaphor. It represents a step toward understanding the fundamental rules that govern how intelligent systems learn from information. Just as the periodic table revealed hidden patterns among chemical elements and transformed chemistry into a predictive science, a similar organizing framework could help transform artificial intelligence from a field driven, largely by experimentation, into one guided by deeper theory. If that happens, the future of AI may not simply be about building bigger machines, but about finally understanding the principles that make intelligence possible.